In this video, we are going to learn about the fundamental theorem of line integrals. So recall that the fundamental theorem of calculus stated that the integral from a to b of f prime of x dx was equal to f of b minus f of a. So if we were integrating the derivative of a function, the antiderivative was the function itself, in this case f, evaluated at the endpoints of the interval, which are the bounds of integration, so f of b minus f of a. We're now looking to extend this theorem to line integrals. So suppose that the vector field f of xy is a conservative vector field with potential function f of xy on a domain D, and C is a curve parameterized by r of t, where t is bound from a to b. Then the integral along the curve C of f dot dr is equal to something in terms of the potential function f of xy, and that is our goal. So step one, since we have a conservative vector field, we can express the vector field as the gradient of the potential function. So this allows us to rewrite the integral along C of the gradient of f dot dr. Now we can define everything in terms of t, like we would normally do to evaluate. So integral from a to b of the gradient of f in terms of t, which we use the parameterization r of t for, dotted with r prime of t dt. That's our dr. So now we can express all of this slightly differently. So we'll say a to b. Instead of writing out the gradient, let's replace it with the gradient vector. So that's the partial of f with respect to x, partial of f with respect to y. Right? The gradient is the partial derivatives. And then we would dot that with dx dt, dy dt as our r prime, thinking about the components as x of t equals y of t equals, then these would be the derivatives, and that's dt. And if we compute that dot product, we have the integral from a to b of the partial of f with respect to x, dx dt, plus the partial of f with respect to y, dy dt, and we're integrating that with respect to t. Now what's in the parenthesis, that's the chain rule. The chain rule of a function in terms of xy, where x and y are both functions of t. This would be our chain rule differentiation. So that allows us to rewrite that expression as the derivative with respect to t of the function in terms of t dt. So essentially, instead of doing it like a chain rule, we could redefine the function in terms of t and just differentiate with respect to t. That's what this is showing us, which then means we have the integral of a derivative. Here's where the fundamental theorem comes into play. So we're going to evaluate the function, the potential function that is, at the endpoints of the curve in this case. So we plug in b to the vector function, so r of b minus the potential function evaluated at r of a. And we achieved our goal of defining the line integral of a vector field in terms of the scalar function, which is the potential function of the vector field, evaluated at the endpoints of the curve in this case. So let's formalize this idea as the fundamental theorem of line integrals, which says C is a piecewise smooth curve parameterized as r of t, where t is bound from a to b, and f is equal to the gradient of the potential function f, be a conservative vector field on D. Then the integral along C of f dot dr is equal to f of r of b minus f of r of a. So if we have a conservative vector field, we know that we can replace the vector field with the gradient of the potential function. So that is really our derivative, right? The gradient of the potential function is the derivative of the function. and we're integrating a derivative. So we evaluate the function itself, in this case the potential function, at the endpoints of the curve. So we can make note, these are the endpoints. Okay, so essentially we took out all of the middle part of our derivation and just focused on the start and the endpoint as the fundamental theorem of line integrals. Now there are a few remarks we can make here. Since the integral only depends on the initial and terminal points of the curve C, this integral is independent of path. Independent of path. Which really is telling us if the vector field f is a conservative vector field and curve C1 and C2 have the same endpoints, then the integral along C1 of f dot dr is equal to the integral along C2 of f dot dr. So essentially, in a conservative vector field, the curve connecting the endpoints does not affect the value of the line integral. Start at one point, end at the other point, doesn't matter the curve you use. So in that case, pick a simple curve, right? Pick a linear path between the 2 points if we needed to. But really, what we're trying to do is use the fundamental theorem of line integrals and use the potential function. The other piece here is if C is a closed curve, then the line integral of a conservative vector field along C is 0, since the initial and terminal points are the same. Right? If we're just evaluating the potential function at the endpoints, and where we start and where we end are the same point, then the potential function will have the same value, and the difference will be 0. So expressing this, right, C of f dot dr equals 0. Now, just to add to this notation, something you may see for line integrals is a little circle on the integral itself. That's not some crazy new type of line integral. That just means that we are integrating along a closed curve. More of a physics notation, but important to see at some point. So all three of these are equivalent. If a vector field is conservative, if a line integral is independent of path, or if the line integral along a closed curve is always 0, or any closed curve is 0 in a vector field, they're all interchangeable. Okay, they all mean that we have a conservative vector field and we're dealing with the fundamental theorem of line integrals. So let the vector field f be a conservative vector field with potential function f of xy being equal to x squared y plus xy squared. Find the work done by the vector field in moving a particle from the point 1, 1 to the point 4, 2. Okay, so to compute work, we're evaluating the line integral along C of f dot dr. But because this is a conservative vector field, that means we can just evaluate the potential function at the endpoints. So f of 4, 2 minus f of 1, 1. And we can write a note to ourselves. This is by the fundamental theorem of line integrals. Notice we don't have to show it's conservative. They told that fact to us, and they already gave us the potential function. So then we evaluate here. So f of 4, 2, that's going to be 16 times 2, 32. And then 4 times 4 is 16. And then minus 1 plus 1. So we get 48 minus 2. So we get 46 as the work done by this conservative vector field moving a particle from the point 1, 1 to the point 4, 2. And notice how the path didn't matter. They didn't tell us the curve connecting those two endpoints because ultimately any curve would give us the same work done. And that's the idea of path independence. So now that we have all of this theorem set up to help us, we need to know when we have a conservative vector field and then also how to find the potential function. So we'll start with the first question. How can we determine if a vector field is conservative? So if the vector field f, which has components p and q, is a conservative vector field, where p and q have continuous first-order partial derivatives on domain D, then throughout D, the partial of p with respect to y is equal to the partial of q with respect to x. Now, let's talk about why this is a fact. If we have a conservative vector field, that means the vector field is the gradient of some potential function, which means that the components are the partial of the potential function with respect to x and with respect to y. So in this case, that's p and q. Now, Clairaut's theorem says if we take the partial of the partial with respect to x with respect to y, that creates a mixed partial that should be equal to the mixed partial in the other order, which is the partial with respect to y, then differentiating with respect to x. And that's exactly what this statement is saying. So this is nothing more than a restatement in a different way of Clairaut's theorem. Right? These are both mixed second order partial derivatives, and if they are equal by the statement of Clairaut's theorem, and remember the derivatives themselves have to be continuous, and that's part of the definition. The next question is, if the partials are equal, is that enough to say that a vector field is conservative and then has a potential function? And that is not enough. We're going to have to fill in a few more steps before we get there. But this could be useful in showing a vector field is not conservative. So take this example, for instance. Determine if the vector field f equals 4xy, 2x squared plus xy is a conservative vector field, and if so, find the potential function. So we already have an inclination that the vector field is not conservative, so let's show why. So we have p and q as the components of the vector field. So the partial of p with respect to y is equal to 4x. The partial of q with respect to x is equal to 4x plus y. So those two are not equal, so that tells us that f is not conservative. Okay, so that's where the above definition is helpful. If the mixed partials aren't equal, then this is not a conservative vector field because it didn't start from a potential function. And if we were using this vector field, let's say in the line integral, we would just revert back to the previous video, go through those steps, and evaluate the line integral the way that we already have learned. So now let's build up to the definition of showing a vector field is conservative so that we know it has a potential function so that we could use the fundamental theorem of line integrals. So a simple closed curve starts and ends at the same point without crossing itself. So a circle is a great example of a simple closed curve. Let's say something like the infinity symbol. That's not simple. It is closed, but it crosses itself, so not simple. Let's say a line segment. That's not closed. And take something like that. That's neither simple nor closed. It crosses itself, and it doesn't start and end at the same point. So if a definition calls for a simple closed curve, think of a circle or something similar. Then we build to a domain, so a simply connected domain is a path-connected domain where any simple closed curve can be continuously shrunk into a point while remaining in the domain. Informally, this means the domain consists of one piece and has no holes. Okay, so the idea here is draw a simple closed curve in the domain, and basically you should be able to shrink it, and there's no hole inside, no issues that you're going to run into. Path connected just means take any 2 points in the domain, you should be able to create a path or a curve between those 2 points. So if we want to illustrate a simply connected domain, just draw a region. That's a simply connected domain. If we drew a domain, let's say that had 2 pieces like this, that's not connected. And if we drew a domain that had a hole in it, that's not simple. So those are the two requirements for having a simply connected domain. So now, with all of that established, if our vector field f, which has components p and q, is defined on a simply connected domain D, where p and q are continuously differentiable and the partial of p with respect to y equals the partial of q with respect to x for all points in the domain, then there exists a potential function f of xy for the vector field f on that domain. So notice a few qualifiers before you even get to looking at the partials and if they're equal. You need to have a simply connected domain. The components have to be continuously differentiable on that domain, and then you can compare the mixed partials, right, essentially Clairaut's theorem, to see if we have a conservative vector field. And if all that checks out, then we can go about finding a potential function for the vector field. A good counterexample here that's often used, so a counterexample, let me just fix that color there. So a good counterexample is the vector field negative y over x squared plus y squared and x over x squared plus y squared. That vector field's not defined at the origin, so that would be the hole. So then if you draw the unit circle in that vector field and go to compute the work done by the vector field around the unit circle, it's not going to be 0, where in a conservative vector field, it should be equal to 0. And the reason why is it's not a simply connected domain. There's that hole in the middle. Now that being said, we have so many discussions about domain. We could take the same vector field and shift the domain. Let's say we put a domain restriction that x and y both had to be greater than or equal to 1. Well, in that domain, there now is no holes. So now we can have a simply connected domain and the potential function would work. And the fundamental theorem of line integrals would hold. So that's what the domain is expressing in all these definitions. But this vector field is an example of a vector field that is not simply connected because there's that hole at the origin. Okay, so now that we've established how to check that a vector field is conservative, why is that helpful? Well, the evaluation of the line integral of a vector field along a curve can be simplified. If we know the vector field is conservative, we could either integrate over a simple path between the given endpoints. So that's the idea of path independence. Or, really the theme of the video, find a potential function and use the fundamental theorem of line integrals, which I abbreviated here. And that's really what we want to try to do. So then the next piece is, how do we find that potential function? So first thing, we want to check that the vector field is conservative on a simply connected domain. Maybe they state that for us. Maybe that's something we have to check. Then we're going to integrate p with respect to x to find a possible potential function, but we need to add this function in terms of y because the derivative with respect to x would have been 0. Then once we find this, we're going to differentiate with respect to y, set it equal to q, and then figure out what g of y is by integrating. Okay, so these are really just some outlines to refer back to. Let's do an example to walk through this and make a little bit more sense of it all. So determine if the vector field f, which is 3x squared plus 2y, 2x plus 3y squared, is a conservative vector field, and if so, find the potential function. Okay, so this is p, this is q. So the first thing we're going to check for that conservative question is the partial of p with respect to y is equal to 2. Partial of q with respect to x is also 2. Since they're equal, the answer to the question is yes, we have a conservative vector field. Essentially what we're doing is we're assuming that this vector field was created from a potential function, so that p is the partial with respect to x, q is the partial with respect to y. We're checking the second order mixed partials to see if they're equal, so that Clairaut's theorem holds, and then we know that that function we assumed existed actually exists. So then how do we find the potential function? So p is really the partial with respect to x, so that's 3x squared plus 2y. Q is the partial with respect to y, so 2x plus 3y squared. So step 1, to find the potential function, we're going to integrate with respect to x. So we're going to get x cubed plus 2xy plus some function in terms of y, whose derivative with respect to x would have been 0. So that's our possible potential function. Then we're going to take the partial of that with respect to y. So that's going to be 2x plus g prime of y. And we're going to set that equal to q. So 2x plus 3y squared. So that means g prime of y equals 3y squared. So we can integrate both sides with respect to y. So we get g of y equals y cubed plus c. We do have an indefinite integral, so that plus c has to come along at some point. So our potential function is f of xy equals x cubed plus 2xy plus y cubed plus c. So how does that help us? Let's look at an example with that same vector field. So evaluate the integral along the curve c of f dot dr. Same vector field, and c is the vector function or the curve defined by r of t, which is 3t minus 2, t squared plus t, where t is bound from 0 to 2. So essentially, because we know we have a conservative vector field, instead of doing f dot dr, we're just going to evaluate f of r of 2 minus f of r of 0. We're going to evaluate the potential function at the endpoints. So we already have our potential function, right? So this is the fundamental theorem of line integrals at play. So our potential function from the previous slide was f of xy equaling to x cubed plus 2xy plus y cubed plus c. We need endpoints, and we're going to get those endpoints by plugging 0 and 2 into our vector function, into our parameterization. So r of 0 is negative 2, 0. R of 2 is 4, 6. These are the endpoints. Now I know they're in the form of a vector because they're the outputs of this vector function that's parameterizing the curve. But do you remember in our work with space curves, we graph the space curves as the endpoints of vectors from the origin. So really the points we're looking for are these vectors in point form. So the integral that we're trying to compute is f of 4, 6 minus f of negative 2, 0. So plugging in, we get 64 plus 48 plus 216 minus negative 8 plus 0, which gives us 336 as the work done by this particular conservative vector field in moving something from the point negative 2, 0 to 4, 6. Again, the path does not matter. Right? This parameterization had no effect other than being helpful in finding the endpoints. Another example, evaluate the integral along curve c of e to the y cosine x plus 2 dx plus e to the y sine of x dy, where c is the line segment from 0, 0 to pi over 2, 1. So this line integral is in differential form. So this is our p, this is our q. Those are the components of the vector field. So the first thing we need to check is if this is conservative. So partial of p with respect to y is going to be e to the y cosine x. Partial of q with respect to x is going to be e to the y cosine x. So they're equal. So yes, we have a conservative vector field. So that means we can either choose a simple path, which a line segment is a simple path, or the fundamental theorem of line integrals. So let's choose the second choice. So next up, we need the potential function. Okay, so we're assuming the partial with respect to x is e to the y cosine x plus 2. And then the partial with respect to y is e to the y sine of x from the potential function. So we'll start by integrating with respect to x. So integral of e to the cosine x plus 2 dx gives us a possible potential function of e to the y sine of x plus 2x plus some function in terms of y. Then we differentiate that with respect to y. So we get e to the y sine x plus g prime of y. And that's equal to q, which is the partial with respect to y. So e to the y sine of x. So that means that g prime of y equals 0, which tells us that g of y equals a constant. Whatever constant it is, we're not sure. So our potential function then is f of xy, which is equal to e to the y sine of x plus 2x plus c. So then to evaluate, we'll just write p dx plus q dy. We don't have to copy the whole vector field. We're evaluating the potential function at the endpoints. So that's pi over 2, 1 minus the potential function evaluated at 0, 0. So we get e to the first, which is e, sine of pi over 2 is 1, so we get e. Then 2 times pi over 2 is pi. We don't need the plus c. I should have mentioned in the last example, because we're subtracting, the c's would cancel out. And then at 0, 0, we have 1 times sine of 0, which is 0. And then plug in, we get another 0 term. So we just get e plus pi. Okay, so this is what it looks like to evaluate with the fundamental theorem of line integrals. Now, most students get tripped up because they think using this theorem avoids integration. We are still integrating. We're just choosing a different integration step, finding the potential function, instead of evaluating the line integral directly. Regardless, we're still integrating to solve this problem. It's just a different approach. So the last thing we need to talk about is a three-dimensional vector field. So find the potential function of the conservative vector field, f, which is 2xy, x squared plus 2yz cubed, 3y squared z squared plus 2. So they do tell us that it is a conservative vector field, so we do know the potential function exists. To show a three-dimensional vector field is conservative will come up in one of the next videos. We have a few ways to do that, but we're not concerned with that yet. Here we're just looking for the potential function. So components are p, q, and r. If this is a conservative vector field, that means each of these is a partial with respect to x, y, and z of the potential function. So the partial with respect to x is 2xy. Partial with respect to y is x squared plus 2yz cubed. Partial with respect to z is 3y squared z squared plus 2. So we're just going to add another step in. So start by finding the potential function. Now it's of three variables by integrating with respect to x. So that means that f of x, y, z equals x squared y. But now g is a function of y and z. Could be y squared z, y plus z, we're not sure. But we can have y and z terms whose partial derivative would have been 0 with respect to x. Then we differentiate that with respect to y, so that's x squared plus the partial with respect to y. And that's going to be equal to x squared plus 2yz cubed. So that means the partial with respect to y equals 2yz cubed. We can integrate both sides with respect to y, and we would get g of yz equals y squared z cubed plus potentially a function only in terms of z, whose partial with respect to y would have been 0. And now, so right now, at this point, our potential function is x squared y plus y squared z cubed plus h of z. So then we can differentiate that with respect to z. So 3y squared z squared plus h prime of z equals 3y squared z squared plus 2. So h prime of z equals 2. Integrate both sides with respect to z. H of z equals 2z plus c, that indefinite integral there. So we put that in, f of x, y, z equals x squared y plus y squared z cubed plus 2z plus c. And now we have the potential function of this vector field. So if we wanted to evaluate a line integral using this vector field, we could use this potential function and use the fundamental theorem of line integrals. So a lot of content, a lot of definitions. Make sure to read those over. Practice showing a vector field is conservative. Practice finding that potential function and ultimately using the fundamental theorem of line integrals. And I'll see you in the next video.